So what we're doing now is we're really shifting our topic quite a bit. Although what today we're doing is still tied to differentiation, but from a very different point of view. So here's a question that we can ask. Okay. So let's ask, what is a function f of x? So its derivative f prime is 3x squared plus 2x minus 5. So this question is very much the reverse of everything we've done to this point. We've been doing, here's a function, what's its derivative? We have all these derivative rules to find those, and we use the derivative for a lot of stuff. This is saying you had some function, you differentiated, and this is where you ended up. Where must you have started? And to answer questions like this, we'll eventually see some specific rules which can help put things together, but also we've done a ton of differentiation, so think, when have I ended up with this? And if we think about when we ended up with 3x squared, you can see, well, this looks like I just used the power rule, and it looks like I started with x cubed. Kind of the same thing for 2x. I've used this in a ton of examples. This looks like you just used the power rule on x squared. For the minus 5, we need to think, when did we end up with just a constant? And that was when we had just an x, and we dropped the x and just kept the coefficient in front. So if you ended with minus 5, then you must have started with an extra factor of x, minus 5x. And given this function, one thing that I really suggest, especially as we're getting used to this reversing all the rules we've been doing, is check your work. Say if I started here and I differentiate, do I get back here? And that version is the way that our brains have been trained this whole semester, using the power rule. The 3 comes down, we get 3x squared. The 2 comes down for 2x. We drop the x, we get minus 5. So this checks out. But here's another different question. What is another such function? So what is another function that has this 3x squared plus 2x minus 5 as its derivative? And at first you think, well, I don't really know, because each of these 3 terms, we figured out where it comes from, and it's not clear what else you can do. But there is something you can do. And so for instance, we could say x cubed plus x squared minus 5x plus 9. And then you might say, okay, sure. What happens is if you add this 9 here, when we differentiate, its derivative is 0, so we're only left with the derivatives of x cubed, x squared, and minus 5x, and that gets us back to where we wanted to be. But then you could say, well, there's nothing special about 9. You could pick whatever number you want, and all of those are functions that have this as its derivative. So for any constant c, you could take x cubed plus x squared minus 5x plus c, and that works. So in fact, this question, what's a function with this as its derivative? There are infinitely many different questions for all the different choices of C that you pick. They're all basically the same, but they are, for different C's, different. So then having gone from there's one function to there's infinitely many, one for every choice of C, the question is, are there any other functions? And in fact, the answer, and this becomes more surprising if you think harder about it, the answer is actually no. The only functions that have 3x squared plus 2x minus 5 as their derivative are functions that look like this. This basic function plus some different constant C. So there are a lot of different answers, but there's essentially one main one, and then you adjust that to get other ones. And in general, this is a fact which showed up earlier, but we didn't do a lot with it. But this is where it really has something to say. It's true that if you have two functions where their derivatives are equal on some interval, then f of x is g of x plus some constant. And so this is saying in general, if you have two functions with the same derivative, they can only be off by a constant. Or, in other words, saying for this type of question, there's one main, or if you find one answer, you can get the rest by adding different constants on. So this fact lets us answer a question which seems much more daunting than this question that we started with. So what if we said, let's try to find all functions f of x so f prime of x equals 2 e to the x plus cosine x. So this word all seems a little intimidating, find every single function that there can be. But what this is saying is that finding all functions is not really any harder than finding one. Because if you can find one, then add on different choices of constants, and that gives you all of the rest. So this, again, comes down to what is a function that has this as its derivative? And in this case, what we really need to do is think about these derivative rules that we have and see if this is where we ended up, what must we have started with? So 2e to the x. Well, we know when we differentiate, if there was a 2 that started there, that 2 is brought along when you differentiate. So this 2 could be in where we started. E to the x. E to the x is its own derivative. So if you started with e to the x, that's what you had after differentiating. So we can say this first term comes from 2e to the x. When you differentiate, nothing happens. So if this is where you ended, that's where you must have been originally. For cosine, what we know is that cosine and sine are in this cycle of derivatives. And what that cycle looks like is we have a sine, that goes to cosine, that goes to negative sine, that goes to negative cosine, and then that goes back to the top. And so if we ended with cosine, what this says is we want to reverse this process and say, we must have started at sine because differentiating pushed us down in our cycle. So we get t dx plus sine x. That's one function that works. And as a quick check that is easier or fits with the way we've been doing things, if you start here and differentiate 2e to the x, the 2 stays there, e to the x doesn't change, sine becomes cosine. That fits is the direction that we're used to. But then that's not all, because we want to find every function, and this isn't all, but it's not, it's basically all. This is one function, but we could say add on some c here. And that's how you get the rest of it. So every function that has this as its derivative has to look like this: 2e to the x plus sine x, then you pick the constant, or different choices of constant gives you different functions. Questions about either of these problems? So this version, for this type of question, the key to it is really very much knowing the derivative rules so well, you can do them in reverse. So very literally knowing derivative rules forwards and backwards. Backwards and forwards, I guess. And for this kind of question, there's some terminology and notation that we're going to be using, but the main mathematical question is saying, here's a function, where must you have started if you differentiated and get here? So the word that we'll use for this differentiating backwards is that the function capital F of x is an antiderivative of little f of x if the derivative of capital F is little f. So that's really what we've been doing here. Saying given a function, find its antiderivatives is find the functions that you differentiate to get here. So we're differentiate backwards. A word in here which is small but does mean a little something is there's a word and here, meaning you can have more than one antiderivative. And that's because different choices of constants give you different antiderivatives. So there could be a lot of antiderivatives, but because they all basically look the same, we try to lump them into one idea. So we'll also say that if capital F is an antiderivative of little f, then what we'll call the general antiderivative of f is the capital F of x plus c. And so that's like what we were doing here. The general antiderivative is find one function that works and then say we can get all the things that work if we allow for some plus c, some constant, which you can pick different constants. Another word for this general antiderivative is also called the indefinite integral of f. For reasons to be kind of explained, but that's another word for it. And the kind of symbolic notation for this is that there's this kind of long curvy s. This is called the integral sign. This is really saying find the antiderivative of what comes next. So we have the integral of f of x dx. And so this would be this capital F of x plus c. That's what this symbol means. Find the general antiderivative, the one antiderivative plus some constant. And in this notation, the two pieces to focus on are there's the function that's saying this is the function that we're looking at. And then there's this integral sign saying find the antiderivative of this f of x. The dx here, at least until the very end of this course, is really just sort of a piece of notation, which is just part of it, and we carry it around. The significance is this is saying the variable of your function you're integrating is x, which we'll see some use later, but it also shows up if you have more than one variable, then that is kind of telling you which variables you're working with. But that's more of a count 3 topic, so it's, for now, the dx is a piece of notation. It doesn't do a lot, but it's part of it. So there are a lot of different ways of asking the same question using some of this terminology and notation. So for instance, here are 3 ways of asking exactly the same question. So we could say, let's find all f of x. So f prime of x equals x cubed plus 4 minus sine x. So this is the kind of question we've answered before. Here's this function, find the all of the antiderivatives. Another way of phrasing this question is to find the general antiderivative of this function x cubed plus 4 minus sine x. The way we're using f is a little bit different here. Here, this is saying you want to find the functions, and this is the derivative of that function. This is saying you're starting here, and then you want to differentiate backwards. You want to anti-differentiate. And these are also the same as saying, let's evaluate the indefinite integral, which is the integral of this function, x cubed plus 4 minus sine x dx. So these are all saying to do the same thing. Find one antiderivative and then add this plus c to say this is all of the antiderivatives. But to do this, we really need to think about how do our derivative rules work as we're going backwards. And I'll lay out some more, in a more systematic way, some of these derivative rules. But for now, we'll just sort of work through them from what we know. So x cubed, like that first example, you think this comes from the power. But your first guess would be x to the fourth, and that doesn't work, because if you try the power rule on that, you have the constant 4 coming down, and there's not an extra constant here. So in a lot of these antiderivative rules, we have to accommodate for some of these extra constants that show up. And what we can do is say, well, if we differentiate this, we get x cubed, which is the right power, but there's a constant we don't want. So what we can say is, if we started instead with this, that 4 in the denominator is there exactly to cancel the 4 that comes down from the power rule, and all you're left with is the x cubed. The 4 here, like in our first example, if you have just a constant, where that must have come from is with an extra constant x. And then sine, again, like we did before, we had this cycle of sines and cosines, and negative sine in there, if you went up a level, that gets you to positive cosine. You could also say just focus on sine. That's at the top of the cycle and that goes backwards to the bottom, negative cosine. But then the negatives cancel and you again get positive cosine. So there's more than one way to sort of come to that conclusion, but either way you get positive cosine. So that's one function that works, but all of these are saying we want the whole family of functions, which means it's this main one, but you add on this plus c. And as we do more of these, what you'll start to feel is the plus c becomes more of a nuisance than anything. It's this thing that, like, oh shoot, there's a plus c, I lost half a point on this 10-point problem or something. But it is really important because these are saying we don't just want one, we want all of them. And the fact is that you get all of them by saying we can add on different constants and those give us different antiderivatives. Questions about anything so far? Yes.
What if you were to like have a question that like, is there some trig identity that equals cosine?
So there are some of these trig identities. So there's one that sine squared plus cosine squared equals 1, and you could solve this thing for cosine, and it'd be cosine is the square root of 1 minus sine squared. Right.
So what if we like took the derivative, or what if somebody took the derivative of square root 1 minus sine squared x, and then that was like f prime, and then they turned that into cosine?
So I guess what can happen with these trig identities is they can look different, but they are in fact going to be equal. So what you can say is, given that these things are equal, what should happen if you take the derivative of this, so cosine, we know that derivative is negative sine. What will happen is if you take the derivative of this, it'll look like a big mess. But if you do some simplification, you will get to negative sine. So one thing that can happen is you have two functions which look different, but are actually the same. So here's an example of that, which we won't really get into, or we won't go too far with, is what is the integral of secant squared? So secant squared is what comes out of tangent. And in this case, there's not really a way to get there other than knowing the derivative of tangent is secant squared. So the integral of secant squared takes me back to tangent. So this is one thing that's true. What you could also say, or a related question is, what if I wrote this integral down? The integral of 1 minus tangent squared. So we'd look at this and say, I've never seen tangent squared come out of any derivative at all. I have no idea, which is a totally reasonable kind of position to take. The way that you could make sense of this is that, in fact, these two functions are equal to each other. Take this Pythagorean identity, divide everything by cosine, and turn it into secants and tangents. You can see that these things are equal. So, right, I guess the takeaway is with trig identities, you can have very different looking functions, which in fact are equal to each other. And that doesn't cause any problems because they are actually equal to each other. But what happens, and this idea, we're not going to come back to this. This actually shows up in calculus 2 using some trig identities. How that's useful is, given something which you don't know, you can trig identity it into something that you do know, or that we're able to do, and then we can find the integral there.
All right.
Yeah, so trig identities, that's a good question, but it doesn't cause any problems. And actually, it's good that different looking things are equal, and so we can as another sort of indication of a direction that we're not going. A lot of what we're going to be doing is very much taking the derivative rules that we know and reversing them, until essentially the last few day or two of the course, we'll see something a little bit different. But for instance, something that we won't do is an integral like this. So what we need to be careful of is, just like differentiating, there's the product rule that said you can't just take two things multiplied together, take their derivatives and multiply those together. It just doesn't work. The same thing doesn't work going in reverse. So how you deal with this is not just look at x and e to the x separately, find their antiderivatives and multiply them together. You have to do something else. In these cases where you have to do something else is really reserved for calculus 2. We will see plenty of integrals here, these antiderivatives, But some of the more involved techniques are saved for later. And what's sort of weird is that differentiation, we can take the derivative of pretty complicated things. Like we have the chain rule, the quotient rule, the product rule, and we can just turn the crank and handle a lot of complicated derivatives. Something like this, we're not going to get to because it takes something that we could understand, but is just, we're saving that for later. So that's a lot of talk about things that we aren't really going to do. What are some things that we can do? So here are some general rules. In addition to, and the textbook has these, I'm not going to write them down, but just taking derivative rules and reversing them. We'll look at a couple more general rules for anti-differentiation. The first thing is, what's the reverse of the power rule? So what if we try to integrate x to the n? So we saw what is a template right here. We had x cubed, and when we anti-differentiated, we got x to the 4th over 4. That template is what happens. The power rule says bring a power down and then decrease it. We take those two steps and reverse them. What we're going to do is take the power and increase it. So like we went from 3 up to 4, and then take that new power and divide it. So divided by n plus 1. But with this, there is a case where this doesn't work. In particular, if n is -1, then this says we try to divide by 0, and that doesn't fly. So this works as long as you're not dividing by, as long as your exponent isn't -1, which is the case 1 over x. What happens in that case, if n is -1, is the natural log of the absolute value of x. So to break that second case off on its own, the integral of 1 over x, which is x to the -1, is the natural log of absolute value of x plus c. And from some point of view, this is our integral rule. This is what we're going to use. But you could also ask why. Why does this absolute value show up? And there are two answers to this. One, why is it true? And two, why do we bother doing it? So the first thing is this function, the natural log of the absolute value of x. If we think about what this is, the absolute value is x if you're positive and negative x if you're negative. So this is another piecewise function that is just the natural log for positive things. But if you put in something negative, it adds an extra minus sign and makes it positive. And what you can check is that for either of these functions, both of them have as their derivative 1 over x. The natural log, that's our standard derivative rule. This natural log of minus x, it's a little chain rule problem, but what you'll see happens is the minus signs cancel and you do get just 1 over x. So that's why it's true. But then also, why do we care? Why do we bother putting this absolute value in? The reason for that is think about the domains of these functions involved. The natural log of x, you can't put negatives into this. This only makes sense for positive numbers. But 1 over x and the natural log of the absolute value of x, those are defined as long as you don't put in 0. And that's why this is worth doing. This says when we're integrating, we go from something which is defined everywhere. If we only use the natural log, we lose half the numbers that we would like to be applied to. And putting this absolute value says we don't lose half the function. We still have a problem at 0, but both of them have that same problem. So there's some justifications for this, but if you like, this is just the rule. Don't forget the absolute value, and that's where we'll be. For a couple other rules, the first two we've really used already. So we could see the integral of f plus or minus g. The examples we've seen have had a couple things added or subtracted, and the way we did it was we dealt with each of them separately and added them back up. And that always works. The integral of f plus or minus the integral of g. And really it works because it worked going forwards differentiation. It works backwards for anti-differentiation. And then similarly, if we have an extra constant here, so we've had like an extra 2 or something, some number in front of our functions, the way we dealt with that was focus on the function and then the constant, just bring that along and multiply it by whatever the antiderivative is. And the last kind of general rule is, what if you have a function with an extra constant inside it? So if you were differentiating something like this, this would be a small chain rule problem. You would take the derivative of the outside, but then you would have a second part that says take the derivative of the inside, and that would give you an extra factor of a. So that's what the forwards direction using a chain rule would give you. We would try, if we want to find the antiderivative, to reverse both of those processes. So what happens is that we'll get f of ax. So this f, find an antiderivative. But then, where the chain rule would have us multiply by an extra factor of a, if we're trying to reverse everything, we're going to divide by an extra factor of a. And then don't forget the plus c. So let me transfer this over. And then I'm going to write a couple examples on the board and give you a minute or so to think about them a little bit. And then we'll talk about these problems together. So this is our integration. So integral 3x to the 5th see the integral of 1 over x squared. The integral of 4 square root of x plus secant tangent. Then let's also squeeze a few in over here. Let's try integral cosine of 3x, and then the integral of e the 5x plus 4. Yeah, I would love to give you some time to work on these, but we don't have enough time. So let me talk about these guys. Yeah, and so I'll go through these and let me know if you have any questions. I'd be more than happy to clarify anything. But like really with learning derivative rules, the way to understand these anti-derivative rules is not seeing me work through examples. It really is working through some examples on your own and starting to make the connections of how we reverse all these derivatives. So in this first case here, the two things going on, there's that 3, that's a constant that we just bring along. The x, so we focus on the x to the 5th, which is our power. So we have the 3. We increase the exponent by 1. Then we divide by the new exponent. And we can clean this up a little bit, multiplying these constants together. Get x to the 6th over 2 plus c. And I'll say this once and not again, but you can always, to make sure, differentiate and check that if you take the derivative of this, this is where you end up. And using the forwards power rule does get us to here. In the second example, one thing we can't do is just focus on the x squared on the bottom. So like with differentiation, what we'll need to do is turn this into a negative exponent, and then with a negative exponent, we can use the power rule. So still an integral, not finding the antiderivative yet, write this with a negative exponent. And then with the negative exponent, be a little careful to make sure that you're finding the right numbers here. When we add 1, we go from -2 up to -1. So the new exponent is -1, and we divide by that negative exponent. And then we can rewrite this as a fraction, putting the negative on top, the x on the bottom. So we get -1 over x plus c. In the next case, the secant tangent, the only way to really deal with this is to think we have these trig derivatives, which one gave me secant tangent? And that is secant. And there's not a way to do that other than knowing that the derivative of secant is secant tangent, and then reverse it. For 4 square root of x, this is similar to the second example. Think of x of the square root of x as x to the 1/2, and then we can use the power rule. So this is 4x to the 1/2. And like with derivatives, there are fractions. Be a little bit careful. In particular, you're going to divide by the new exponent, which means you're going to divide by a fraction. So we get 4. The new exponent is 1 bigger, giving us 3/2. And then we divide this by 3/2. So if you like to flip that fraction and multiply, instead of dividing by 3/2, multiply by 2/3, and we get 8/3 x to the 3/2 plus secant plus c. Questions about any of these 3 examples? So for these second 2 over here, the first one is this third rule here that says we have a function, but there's an extra constant on the inside. And so what this is saying, and I think that this rule clarifies what is going on here, is first find the antiderivative of the function. So cosine, we think about all the derivative rules, cosine backs up to be positive sine. So the cosine becomes sine. The 3x that was inside stays inside. But then the 3 that was inside, we divide by that. Said I wouldn't say it, but I am. And if you differentiate this, what happens if the sine becomes cosine, and the chain rule brings out an extra 3, which cancels with the 3 in the denominator to give us no constant up there. The very last thing, and I'll knock this out quickly, this is kind of the same deal. The integral of the e to the x doesn't do anything. So we get e to the x again, or e to the 5x. But because there's a 5 in here, we have to divide by that to counter what the chain rule would do if you were to go forwards. And the last thing with 4 to the x there, we need to think about what is the derivative rule for exponential functions look like. The derivative of 4 to the x is 4 to the x again times a natural log of 4. So this is a different kind of rule than the power rule, but it's kind of morally the same. This derivative rule gives us an extra constant that we don't have here, so we need to adjust where we start to account for that. So what we want to do is, in fact, instead of we get the same thing and multiply by an extra constant, we get the same thing and we divide by an extra constant. Because if we differentiate this, the 4x stays the same, but we get an extra factor of natural log 4, which cancels with the factor in the denominator. Okay. So hope, I guess, this gives you some idea of how these examples work. But again, the real way to understand them is to work through some examples. So take the homework for this seriously, not that it's the most difficult homework we've had, but you do want to make sure that you're training your brain to reverse all these derivatives. Okay, so that's it. And I'll see you all on Friday.